Good morning, everyone. I am here to present our research paper titled Multi-Layered Cybersecurity for Smart Power Grids Using AI and Machine Learning for Real-Time Threat Detection and Prevention. This work has been carried out by myself, Saket Kumar Mishra, and Professor Krishna Bihari Yadav from the Department of Electrical Engineering, NIT Jamshedpur. The motivation for this work is the increasing vulnerability of modern smart grids to cyber attacks due to their heavy reliance on IoT, sensor, and communication technologies. As smart grids evolve, they are becoming a double-edged sword. On one hand, they provide efficiency, automation, and sustainability, but on the other, they create new entry points for cyber attacks. In this paper, we address three major types of attacks: denial of service, man in the middle, and false data injections. We designed a multi-layered AI/ML based security framework that integrates physical network and application layers with anomaly detection and predictive threat prevention. Our frameworks achieve 98.5% accuracy with low latency and minimal false positive, proving its effectiveness for real-time protection of smart power grids. The research objectives were clear and structured. First one is analyze vulnerabilities in smart grids caused by IoT, CPS, and communication networks. Second one is design a multi-layered framework to provide security at the physical network and application layers. Third one is to implement AI/ML threat detection algorithms such as SBM, random forest, KNN, and neural networks. In this paper, we mentioned all the algorithms and explained the process for detection the threat, but for modeling purpose and simulation purpose, we only used SBM. And fourth one is for simulating and validating these methods, we are using MATLAB Simulink under real attack conditions like DOS, MITM, and FDI. And fifth one is evaluate system performance with matrices such as accuracy, false positive rate, latency, and adaptability. This structured workflow allowed us to move from problem identification to practical implementation. This diagram shows the architecture of our multi-layered cybersecurity framework. At the physical layer, hardware like transformer, RTU, and smart meters are secured. The second one is network layer monitors traffic using IDS, firewalls, and packet inspection to detect attack like DOS and MITM. The application layer checks for anomalies in SCADA commands and operator inputs which prevents FDI attack. Finally, the AI/ML analytics layer adds intelligence enabling predictive detection of zero-day threats. All these layers feed into a real-time intrusion detection and response system, which can automatically isolate compromised nodes or correct tempered signals. This layered defense makes the system resilient and adaptive. Our methodology can be divided into several steps. On the data simulation side, we generated synthetic data set with both normal and malicious traffic using Gaussian noise and binary labels. And model training side, we trained ML models such as SBM and other neural networks. And we integrated this model into a MATLAB Simulink smart grid subsystem. And cyber attacks like DOS, MITM, and FDI were simulated in real time. Our response mechanism of this system is like continuously monitoring inputs, detected anomalies, and triggered automated countermeasures like node isolation and signal corrections. This approach not only improves accuracy but also ensures real-time adaptability. Workflow diagram shows the process visually. We start with data simulation, move on to ML model training, and then build the intrusion detection function. Next, we integrate it into a MATLAB Simulink based smart grid simulation where live cyber attacks are tested. The system then provides real-time detection and automated responses, and finally we validate the result using performance matrices such as accuracy, latency, and false positive rates. Now we can come to the results part. So our framework successfully detected DOS, MITM, and FDI attacks in real-time simulations. We achieved 98.5% accuracy with very few false positives. Most importantly, the system had low latency with response time in order of milliseconds, ensuring minimal disruption to grid operations. This demonstrates that our framework is not only theoretically sound but also practically deployable in real smart grids. We can see our result pipeline. This pipeline explains how the system processes data. Input signals from the smart grid such as voltage, current, and SCADA commands are first analyzed by ML models. Then, if the system detects an anomaly, it raises an alert and triggers automated mitigations. If no threat is detected, the grid continues with normal operation. This dual path ensures both security and operational continuity. Uh, in the real-time threat detection graph, we can show this graph shows the real-time threat detection output. The red spikes represent malicious activity and the system successfully flagged those events with almost no delay. Where the threat, when threat is detected, it is showing 1, or when threat is not detected is showing 0, means 1 is yes, that time threat is detected, and on when it's showing 0, that time threat is not detected. So the model, particularly the SVM classifier, showed robustness and stability, adapting quickly to different input conditions without losing sensitivity. This proves that the system is capable of real-time streaming detection in a dynamic grid environment. You can see offline intrusion detection graph. This graph shows the offline testing results using pre-collected batch data. Here too, the model maintained its accuracy of 98.5% with consistent prediction and minimal false positives. This shows that the frameworks work reliably for both real-time streaming data and offline analysis, making it versatile for different deployment scenarios. Here we are showing the table which compares previous system with our proposed framework. On the security approach side, earlier system were single layered while our is multi-layered. And the threat detection side, traditional system could only detect known attacks. Our system can detect DOS, MITM, FDI and adapt to new threats. On the response side, older system required manual or static responses, while ours enables automated real-time mitigation. On the performance side, our system has high accuracy and low latency, outperforming earlier methods. And scalability of previous system were limited, but our framework is scalable for next generation smart grids. So for to concluding, we have proposed a multi-layered AI/ML powered cybersecurity framework that integrates physical network and application layers with predictive AI analytics. The system successfully detects DOS, MITM, and FDI attacks in real time with high accuracy, low latency, and minimal false positives. In terms of future work, our goal is to extend this framework to address all 12 major cyber threats in smart grids. This include replay attacks, Sybil attacks, jamming, spoofing, malware, insider threats, and others. We also plan to develop adaptive AI models for evolving threats and ensure integration with SCADA EMS system through middleware and hybrid architectures. This will transform our framework into a comprehensive and scalable solution for securing smart grid against all major cyber threats. Here we see shown the some of the references which we have used in our paper. In this slide also, other next references are shown. This slide also consists of few references. So here I am concluding my presentation. In summary, our research provides a robust, multi-layered and intelligent cybersecurity framework for smart grids. It has shown strong performance in real-time detection, and it lays the groundwork for protecting against all forms of cyber attacks in the future. Thank you for your attention. I will be happy to take any questions now. Thank you so much.